everybody. Hope you had a good lunch. Welcome back. My name is Ernst. I work at Intel at the Open Source Technology Center, and I want to talk about Kata today, Kata Containers. And the quick background, Kata Containers, we're looking to provide an extra layer of isolation to provide better security in the container ecosystem. And through that, we're working on the Kata Containers project. I want to give a quick background on what Kata Containers is and why we felt like this was important and why many people felt this was important. And then really, I want to talk about how we leverage QEMU and KVM and kind of maybe get some feedback and kind of highlight some areas where we think there's future work. So really, working on Kata is, especially recently, just turned into what are all the options in the man pages, which itself is quite a long task. But what is a container? Containers are, you have processes running and you're leveraging the Linux kernel to provide isolation. The tools that are getting leveraged, like namespaces, C groups, using capabilities, setcomp filter. None of these have anything to do with containers, really. These are existing solutions for processes and for hierarchies of processes. So namespaces just make it so that way, if you have a couple of processes that you can make it seem like they own the host themselves. They can't see anything from the others within that namespace. So if you look at like a network namespace, a mount namespace, process namespace, it makes it so that way you can't see what maybe your neighbor has or what the host has available to it, which is nice. But you can still see signs of the other person being there. If the other process is using all the CPU, you can kind of feel it from a denial of service. Same thing for memory. So that's where control groups are used to be able to kind of throttle and manage the actual resource utilization per process, or per container in this case. So that's great. And then on top of that, you also have different filters. I call them filters. It's probably not the right word. But that's where I think of like setcomp, where you're saying, hey, these are syscalls that you shouldn't be using. These are syscalls that you're allowed to use. Capabilities. You can't change the routing tables, sorry, or you can't reboot the machine. These are clear, saying things that you should not allow a container to be able to do. So out of the box, you get these for free. Well, you get them. They're not all free, but the main thing that we see is that these are great, but it's a single layer of isolation. There's only a single interface, and that single interface is the host kernel. They all share the same host kernel. And while it's a great layer, we think of it as a single layer. And that's why usually if you were to go to a cloud provider and say, hey, I want to run containers, they're not going to say, sure, we trust you. You have bare metal access. Just go run your container workload. They would give you a virtual machine, and then you can go play as you would like. This is essentially what we're doing with Kata Containers via Crayola. What we're doing is every container workload we're putting inside of a virtual machine, its own virtual machine. Each of them can have its own unique kernel even. You could have a 4.11, you could have a 4.19, you could have a 3.10 for each of those individually. Yeah?
Several containers in the same VM.
So the question is, can you put several containers in a single virtual machine? And yes, if you are using Kubernetes and it's called a pod. But you can't just say, I want to run these 20 random containers in here. There's no, the answer is no. What we're trying to do is not change, and this will kind of get maybe into the next one. Let's just change the slide. What we are is an OCI compliant runtime. So usually you just say docker run blah, and that's it. And now you have an Ubuntu looking shell that you're running in. That's very exciting. And what we want to do is we want to provide extra security, but we don't want to change anything for you or for anybody in the kind of microservices, cloud native design pattern space. Like, we don't want them to have to change what they're doing. This is meant to be hidden from you. You should never know unless you start looking at processes, footprints, things like this, that it's running. So if you're to use Kata, what you would do is, just Docker as an example. Docker, you can set default runtimes. So up there, there's a lot of text. Somewhere it says default runtime, run C. That's like the canonical default standard. So when someone says, hey, Kata, why are you replacing Docker? It's like, well, no, we're not. We're complementing an existing solution within Docker. So run C is an OCI compliant runtime, as is Kata Containers. So you would add it in there, and what it looks like then, this is magical PowerPoint execution. You would see just a container is running when you say runtime equals run C. And if you do it with Kata, is the exact same thing. Only that process that you're looking at is actually inside of a virtual machine. So what does it actually look like? I say Kata runtime, that's the run C equivalent. So if you have an upper layer orchestrator like Kubernetes or like Docker, what it's going to do is you're going to say, kubectl, apply this workload, and it's going to create the workload and then run the workload. Right? So what we do is receive the command that says create it, and then what we're going to do immediately is create a virtual machine. Today we use QEMU, KVM. We have a minimal kernel that's going to boot. Again, we're not using the host kernel anymore. This is the guest, the traditional virtual machine. But it's minimally configured because that's kind of a best practice if you have a container OS. You don't want to have all these features just adding an attack surface, essentially. And also a lighter weight footprint by reducing it. Then we just have a really minimal rootfs that is essentially just starting up systemd and running an agent. This agent is like that run C equivalent, the canonical, like the de facto standard. And all it does is actually handle the lifecycle of creating a virtual machine. So I'm not saying containers are terrible, we should just use virtual machines. I'm saying we should add an additional layer. So we still are using namespaces, C groups. We're looking at and figuring out whether we want to use setcomp on the inside or not. But the upper layer process, the orchestrator, is expecting to see the container. Everything is kind of made to assume that you just have a process running on your host and you're going to interact with it through there. So what we do is we create a shim process, and there's a 1-to-1 ratio, and it's tied to the lifecycle of the actual container process running inside the virtual machine. So that means now they can go and look at what's the standard I/O. What's the standard there? I want to send signals to the container process that I think is running on the host. So this is the way we lie to the orchestrator. And then any signaling that's handled would go over inside to the agent, and the agent would go ahead and kill whoever it needs to kill. We use VSOC. We're using VFIO serial before, but VSOC is a lot cleaner as far as being able to have multiple clients. And it's a gRPC protocol that we use for communicating. So now you guys know everything about Kata containers. I want to start talking about different areas of Kata containers and what we leverage to pretend to not be a virtual machine and to hopefully make it lighter weight. So boot time is a really easy one to kind of look at. It's very, ephemeral workloads, containers, you think you boot it up and it's gone. In like 3 seconds you did something and then it's gone. So boot time is a very clear, it makes sense and it's easy to measure. So some things that we do, we make use of hotplug a good amount. So basically hotplug is allowing us to do things in parallel. So while we are creating the virtual machine, we can start working on preparing the actual container workload itself. And any potential volumes that workload may want, we can prepare them. And then once it's up, we just hot plug them directly, and we use QMP. Similar for any devices, we also hot plug them. If a particular container wants to make use of a GPU, we would hot plug that GPU, so that way it's off that initial critical path. And doing this too allows when people want to start doing tricks like having a virtual machine up there ready to go, but no workload yet. So you can kind of have like a pool ready and then inject workloads into it, so that way you can kind of mask the actual boot time for the virtual machine. So some other things that we do. Today, by default, in our packages, we use QEMU Lite, which essentially means it's QEMU with a couple of patches that we had on top of it. What are you seeing? Yes. And basically what we look to do is not use firmware. We don't want to use firmware. We don't want any extra steps or anything like that. So let's just go ahead and just add what the firmware is doing, put it in QEMU, and then just boot directly to the kernel. This wasn't really a nice thing to maintain upstream, which makes sense. So QBoot was introduced, which essentially addresses all of what we wanted out of QEMU Lite. So this is a firmware that does nothing except for get ready to boot into the kernel and to actually link the ACPA tables for us. So we've been testing this because the deadline of wanting to talk about it here. It works, and it looks fine. So we're going to be looking to move to this as we adjust what type of hypervisor we use. So what about footprint? We have a minimal kernel. I talked about that. Security surface, great idea. Also helps with our footprint. Minimal rootfs, makes sense. A minimally configured QEMU, so when we build it, only the modules that we really need. We also use DAX and nvdimm. And we do deduplication of memory using KSM. So looking at it in a picture, essentially we use DAX, direct execution place. Direct execution. Yeah. And we use that for the rootfs. So the rootfs we put into each virtual machine. So if you have 5 containers, they're going to share the same minimal rootfs. It doesn't really make sense that you have 5 times rootfs size. So what we do is we use DAX for that. And then we also market it for nvdimm. And doing that is essentially saying, QEMU, please, guest, don't cache this. Just use the host page cache instead. So then everybody is utilizing the same bits off of the host. This saves a good amount of memory. While we try to minimize rootfs, this is now amortizing the cost of the rootfs. So the more containers we have, the cheaper it is, effectively. Same idea for KSM, only this is more active now. Essentially, what we'll do is we'll have a throttle KSM where, well, this is an optional thing, but once a workload a container starts up, it'll kind of kick KSM, and KSM will go through and check out the pages and then merge them and then get out of the way. Because scanning pages is CPU intensive, and we don't want to use all the CPUs. So with these two, it's another way to help reduce the footprint. And again, this really depends on the scale and type of workloads that you're using, what you're going to see. So totally other topic now. Let's talk about CPU topology. What we end up doing generally is booting a container, our QEMU, our Kata container, with just a single vCPU by default. And then however many CPUs the workload needs, we'll hot plug in. This helps from a boot time standpoint as well. And now we start thinking about how should we hot plug it? There's really kind of 3 options, and I guess you can permeate on that, so maybe there's more. But first, we can just say, how many threads? Just add a thread. Other option, let's just add a core. Third option, let's just add a socket. So every time you want to add a vCPU, one more socket, please, one more socket, please, one more socket, please. And through experimentation, we saw that just giving a socket is a little bit more friendly for CPU performance on some different testing, particularly when we're looking at network I/O. It was just like a slight measurable improvement. We didn't really see a lot of downsides. I think I've seen other research kind of highlighting that sometimes using just a socket can be a little bit more effective. I'd be curious if people know or have feedback on that, but to us it seems this is the most effective for our use case. Memory. Just like how we do the CPUs, we often will hot plug memory into the virtual machine. Which adding it is fine, but removing it when it's not needed. So sometimes in a container lifecycle, you can have a pod. A pod is a group of containers all working together. In Kubernetes, it's the smallest schedulable, executable bit. And in a pod, you can have some work that gets done at the very beginning and then is never done again. So like in a init container, that'll go and make changes in that pod, and then it'll never execute anymore. So you can imagine that the resource utilization isn't linear in your workload, just like most workloads wouldn't be. So if we can do anything to free up system memory, it's probably a good idea. So starting to look at how we do this, ballooning is one option. And we kind of looked at it. You can return any amount. It doesn't really free any slots. Why do I have to even worry about slots? And now I have to start thinking about, I want to set a max memory then, so that way the balloon can take it away, but then I can add it again if I want. The maximum set of memory, the amount of memory that I give to a virtual machine costs me as far as footprint. So each gigabyte's about 2 megabytes worth of overhead, just kind of imagining all the memory tables for it. If you're nested, it's going to be more at that point as well. So we don't want to just kind of willy-nilly say, like, you guys have a terabyte, but we're going to balloon like crazy, or anything like this. Hot remove is kind of the other option that I was looking at. Well, I'm not looking at. The team is looking at in Kata. And with that, you can free slots, but now you're kind of dictated about how big is a slot actually. But at least I can add memory, and it's kind of consistent from there. What I've heard is that there's some work being done on VFIO-mem, so like para-virtualizing memory. At this point, I can do something seemingly at a much finer granularity. This sounds great, but it's work in progress. So we'll see where this ends up. It seems very attractive for our use case. And I'm curious also, when doing this, if I'm using VFIO and hot plugging PCI devices in, I don't fully understand yet, and we're doing some testing now on what the impact is as far as the DMA, like does that slot that happens to have the address space get locked down? Can I no longer do this hot removal? This is an area that we're still looking at, and I would love to talk about. Speaking of hot plugging VFIO devices, VFIO is great. It's fun, it's fine, and what we're looking at is, depending on the machine type we use, we kind of leave it configurable right now. Right now we support 2, we're adding a 3rd. Maybe we support 3, I don't know the exact right answer for that. But we use PC machine type and we use Q35 machine type. If it's PC, we do ACPI hot plug. If it's Q35, we do PCIe. But in either case, it's a PCIe device, and we're hot plugging it in, but it's getting placed on a PCI bus inside the guest. So what I'm wondering is, does anybody care those lost capabilities in our situation? I'm not really sure. We do know, but I'm not sure how important it is, like some of the error stuff. Yeah?
You should talk to Alex Williamson. There is a long story now about PCI link speeds and everything around this area. In general, it's not recommended to put PCI Express device on the PCI bus, because then guest OS thinks it is a PCI device.
Yeah.
Because QEMU hides
Yeah.
all the PCI.
Exactly. Yeah, so that's what we need to understand if in a container type of workload, is this going to bite us? And then on top of that, it's also, if we had a new machine type, if we could pick, we had all the options, is there a real strong preference, PCIe versus ACPI? From my perspective, ACPI is less, what's the timing of hardware and everything else? I'm not tied to the PCI spec as much, where ACPI seems a little bit more modern, direct. So I'm curious, what the difference is, but from a performance standpoint, we don't see much difference. Yeah?
Sorry, why are you placing PCIe devices on the PCI bridge instead of PCI Express bridge?
This is a good question.
You should talk to Alex Williamson, because he's an expert.
Yeah, let's follow up and talk about that after. I have way too many slides, but I do want to, that's exactly the conversation I want to have. So networking, how do we get I/O in and out? So generally in containers, like the most straightforward basic configuration is you have a vETH on your host, and it drops the other half of that vETH into a network namespace. What we have to do then is take a vETH living inside this namespace and attach it to a virtual machine. There were a couple options that we looked at. MacVTAP is what we have right now. We're also looking at TC mirroring. By default, by default it uses vhost threads as well. I'm not sure if this is the best thing to do or not. I think that Stefan kind of brought up a little bit, like you could use vhost user instead. So that way we're not going all the way to the guest. Now all of a sudden you're in the kernel of the host. But for now, this is what we use. And then we use multi-queue. And I was doing some performance testing around nesting, and then also just in an L1 kind of configuration for Kata. And I saw that basically num queues should be equivalent to the number of CPUs until you get to like 4. After that, maybe you can get a little bit more, but these are resources that are eating CPUs and eating memory that it's really not getting much return. Yeah?
Probably if you use vhost, you need to see where the vhost kernel triads are.
Yeah.
Because they can interfere with vCPUs. You probably can pin them with the
Whenever I look at performance stuff, I know that when you look at this, they're like, okay, the first thing you do is pin the vCPU threads, pin the vhost threads, and start like. If you're doing that, you should be using a VF maybe instead. I'm not sure. Maybe you can use SROV, or maybe you would, we don't give, it's not easy for us to start pinning and everything, because again, this isn't a virtual machine anymore. This is a container, and it'll be hard to figure out how to balance that. But speaking of not using vhost, another way is to use vhost user. So we provide the ability, if you have a vhost user socket. So in this drawing, you wouldn't notice necessarily, I have a namespace, then I just have this socket, and I don't have a network namespace. That's because it's not part of the network namespace. It's not namespace. It's just a file on your system, right? So that one we can just attach directly. So if you're using something like a DPDK or an Open vSwitch or a VPP, any of these things, this is a nice way to get connected inside of a container as well. And then there's physical networking. You can actually just pass the NIC directly in, or pass a VF directly in and use it. So storage. This is kind of there's two different ways that this could go down. It could be really nice or it could be awful, and I don't want to talk about it. If it's block-based, cool. Well, even still, it could be painful. But if it's block-based, default, we use VirtIO SCSI. But we use VirtIO block in the past as well. We've also looked at, can we use vhost user here? Can you start using it something like SPDK? If it's not block-based, it's a file system-based, like something like overlay, then it gets a bit more painful. We use 9PFS. And I don't know how often people use 9PFS, but it might be suboptimal. So some questions as I kind of go through here and try to do some performance. By default, we use VirtIO SCSI. I feel like from all the reading and talking to people, it seems like, all right, this is where the development is going as far as block storage. We have configurable to use IO threads. It's not set by default. I'm still working to see and really get performance impact of this to see. For cache settings, we're using default right now, but I mean, it really kind of depends on the workload. So I'm trying to figure out, should we make that easily configurable per container, or is there a sane default? And also, we've kind of looked at SPDK briefly as well for like a vhost user SCSI type of interface. So that's great if it's block. Again, if it's not block, if you're using something like overlay, which is very popular, you get to use 9PFS. So, lack of general POSIX compliance. How many times I get someone say, hey, I was trying this database workload that nobody would really use, but it's a nice way to quickly poke a database, and they did an mmap, and then I don't have a container anymore. That's happened. It's generally not very performant. A lot of people come and say, I've had someone is running. Well, either way, it's not performant. I don't need an example for that. You probably know that. It's not really particularly well supported. It's not like people are passionate about 9PFS and fixing it. But the good thing is it's available. And that's pretty much what it has going for us, as far as hitting our use case. We're looking at future alternatives. NFS over VSOC sounded like something that would just cure all of our problems. I'm not sure that is the case. But then also, there's some very, very early discussion of, can we make something like a VirtIO FS? So I'm really excited about that. I think that's pretty early on, though. So we'll just keep telling people not to use overlay. Some other stuff around storage is I was doing some nested testing. I did a presentation yesterday talking about the results for it. And this is what it looks like for cost. If you're doing it in an L1, it costs 0.6%. 0.6%, that's less than a CPU. It's a 16 core. Don't worry about it. But if you look at the L2, it's quite expensive. Relatively, we're looking at about a 20x difference between the two. So this has me thinking that the use case when you get into nested, people are excited about nested, is to be passing something from L0 to L2. There is no L1. So we need some kind of way to be enlightened and to be able to pass devices all the way to L2 and not be going through 2 layers of block storage or anything like this. So I think this is a pretty interesting area. And even if you do that, now we have to figure out how the interrupt routing and everything's going to handle. That's still going to be quite an overhead. So I don't know. We'll see.
The VFIO now, so you could pass, the devices.
Okay. So one more area to look at, which is kind of a beefier area, and I've gotten some good feedback from the community before already, is on security. We are providing stronger isolation, so it's pretty fair to say that we should be very concerned about security and making sure we're doing best practices. It's hard. How many containers can you put in a gigabyte? Very important. How secure is something is very it's really hard to quantify. So it's been interesting, and it's always a trade-off, and we're trying to figure out what the best practices should be in having either like an ultra-secure configuration and then a realistic and density favorable configuration as well. So different under the umbrella of security. We ran into issues for a little bit because our containers would essentially block because we're waiting to have enough entropy to give to the virtual machine so it can continue to boot. Or if the first thing your container is going to do is generate an SSH key or something, all of a sudden we have some issues. So that was easy. Just use dev urandom, not dev random. That's fine. Generally, it's fine. For most people, it's fine. If you're that concerned, then you shouldn't be using a container anyway, maybe. I don't know. Enhance security in the guest. So right now, again, keep best practices, keep the rootfs and the kernel as minimal as possible. That's fine. Other things that we're looking at is, we've gotten feedback. Should we apply a setcomp filter inside of it as well? There is a default that would come with Docker and everything else, and they're creating one for Kubernetes now. Doesn't make sense to also run setcomp inside. We can do this, but now we need to include all of the bits for setcomp, which is going to hurt density about 20% or so. So we're trying to fight that trade-off right now, and how easily can we make it optional. Extending identity of the container workload, so using virtual TPM. We don't do this right now, but I think often this is extending the measured boot so that a container can say, what am I actually running on? Including myself as well. So for me, I question how much people really value a virtual TPM, if there's enough trust in that and extending the TPM with a virtual one, but it sounds like people are doing this. So I think it's particularly useful in a container OS where you're not ever adding packages all the time and having changes from the boot. It's very static. Other areas, protecting the host. So running non-root QEMU. We started looking at this. You can make changes. Dev KVM, okay, fine. Dev vhost, okay, we can work around it. The IPFS file system, we can do it through a proxy helper. Block devices, we can do it, but then we have to figure out once the container is gone, we got to assign it back to the original permissions and ownership. So we've been looking at it, and we need to do this. It's hard. libvirt does this already. So I've gotten the criticism like, how are you guys not doing this anymore? So we were scared of libvirt initially. It's too big, XML, what am I going to do with this? It's going to add complexity. We use GoVMM right now, but we see now there's Go bindings available for libvirt. So we're starting to investigate and look at it and see, this is something we should look at because apparently it's going to solve all my problems in the world. So, and similarly, if I want to constrain QEMU itself. So cgroups namespaces, oh, okay, they do this already. We should look at it. I just don't want all of libvirt. I just want what I want out of it. So we need to really look at that. And then the last thing that we're looking at is reducing the code footprint for the actual hypervisor itself. And this is another project kind of outside of Kata, and I'm a consumer of it, and I'm excited about it for how many, essentially getting rid of as many using a new machine type that really eliminates emulation as much as possible. So like a no emulation hypervisor with minimal devices available and everything else. So there's a talk after this about that. If you don't leave, you'll hear it. I think it's pretty interesting. So that'll help as well from a footprint and everything else. But if you want to learn more, you want to contribute, you want to make libvirt work well with Kata, You can find us. We're all over the place. So. And that's all I have. So feedback, questions for a few minutes, and then I would love to talk more afterwards as well. I'm leaving now, so don't talk to me. Yeah.